Howdy, this is Diego Cansino for the video assessment number 1, and I'll be explaining how to figure out or see correlations to enthalpy and figuring out measurements related to our solute, solvent, and solution, such as freezing points, boiling points, and stuff like that. And let's get into it.
Okay, howdy. All right, so to make things simpler, I went ahead and labeled that anything that is bolded and green will be the answer. The blue is kind of just the process to solve the problems. Okay, so starting off with number 1, it's asking to describe the enthalpy changes and when they mix. So the enthalpy changes going on is that there is, for delta H of the solute and delta H of the solvent, they're both undergoing a endothermic reaction because they're both breaking their intermolecular bonds in both the solute and solvent. And so when they actually mix, it's when both have broken up and now they are mixing together, undergoing an exothermic reaction, right? So now that the dextrose, I believe I'm saying that right, the dextrose and the water have broken up, they mix together, which is an exothermic, and that's when they bond, after they are broken up. And what is the solute-solvent interaction in the solution? The interaction between the solute and the solvent is the bonding of the two polar molecules, because they're both polar molecules, right? And so they'll bond together, and their strongest bond that they'll be making because of their OH groups will be the hydrogen bonds, right? And so also, like, I believe this relates to like dissolves like, where because they're both polar, that's what they'll break each other up and like they'll mix together. I believe like that. And but yeah, so the interaction will be hydrogen bonds because of those OH groups. And going on to question 3 here, calculating all these different terms. So starting with molarity. Molarity is defined as the moles of solute over the liters of solution. And so we're given grams of our solute, right? And we will convert that to moles, and we need to find the liters of the solution. And so in order to do that, we have to find the total solution in grams in order to convert, right? And so we find our total grams. This is the 5 grams plus 100 grams, which we could figure out from the water, and its density of it being 1 per milliliter, sorry. And so after plugging that in, we have our moles over the liters, which gives us the 0.2685 molarity. Going on to molality, it's defined as the moles of solute over the kilograms of solvent. So we already found our moles earlier in this first question, right? And so we get to just plug that into the numerator. And then we plug in our kilograms of solvent, which we know we have 100 grams of water, and we just convert that to kilograms. And after conversion, we get 0.1 kilograms, right? And so we just plug that into our formula. So we have the moles divided by that 0.1 kilograms of solvent, and we get 0.2775 molality. Going on to part C, we're looking for the mole fraction of dextrose, which is defined as the moles of the solute divided by the moles of the solute plus the moles of the solvent. So basically just the total moles. Once again, we already know the moles of our solute, which is this 0.02775 divided by our known moles plus the moles of the solvent, which is the water, and we just convert it here. So the 100 times the 1 over the molecular weight, I believe, or the 18.01 grams per mole, right? And so plugging that in, you could divide that and you get 0.00498 for the mole fraction of dextrose. Going on to part D, for the mass percentage of dextrose, it's defined as the mass of the solute divided by the mass of the solution. So we know our mass of our solute, which is 5 grams, divided by the mass of the solution, which we figured out back here in part A, which is the 105. times 100%, and you end up with 4.76%. Going on to the E, it's ppm is defined as the mass percentage times a million. So we take our mass percentage before we multiply it by the 100%. So the 5 divided by 105, and we get this 0.0476 times a million, which is just 10 to the 6th power, and we get 47,600 ppm. Same thing for the billion, except we're multiplying it times a billion, which is 10 to the 9th power, and we get 47 million, I believe, 600,000. And for question 4, it's giving us the pressure, and it's asking us the vapor pressure of the solution. So it's defined as the vapor pressure of the solution equals the mole fraction of the solvent times the pressure of the solvent. And so we know that dextrose is a non-electrolyte, meaning that we could use that formula of 1 minus the mole fraction of our solute, which we found back here in part C, which gives us 0.995 mole fraction for our water, which is our solvent. And so we simply plug it into our formula of that 0.995 times our given pressure, and we get 92.19 torr as our vapor pressure. And number 5, the boiling point. So it's defined as delta T equals the I times the constant times molality. So we plug in the 1, we plug in that constant given to us, and we plug in our molality that we found back in part B, and multiplying that, you get 0.142 Celsius. And then after that, after you figure out that, we have to add it to the initial boiling point, which the initial boiling point of water is just 100 Celsius. So after adding that, you get 100.142 Celsius. Number 6, what is the freezing point of the solution? We have our similar formula, except we're going to use it to find the freezing point. So once again, plugging in that into the I, which is just 1, plugging in our constant, which is 1.86, and then plugging in our molality, we get the 0.516. But instead of adding it, now we're going to take away from the initial freezing point. And the initial freezing point of water is 0. So 0 minus our given number, it's negative 0.516 Celsius for the new freezing point. And for osmotic pressure, sitting at 25 Celsius, osmotic pressure is defined as the I times the MRT. So we know the I is the 1, and we know this M will be our molarity, which we found back in part A. Molarity, so we plug in that, and then for the R, it's just the constant. This is a constant that will always be the same, so the 0.08206 times the new temperature that we have to figure out. So if it's at 25 Celsius, we have to add 273.15 in order to convert it to Kelvin. And so plugging in everything into the formula, we have 1 times our molarity times our constant times our new temperature in Kelvin, and we get 6.57 ATM. And that's the final calculation for the final question, and thank you.